If you look inside the Linux kernel source code, you will find code for networking, code for memory management, and code for file systems, but you will search in vain for a container object. The truth is, Docker doesn't exist, at least not in the way we think it does. When we talk about Docker or containers, we're actually using a high-level UI for three specific Linux kernel features: namespaces, control groups, and union file systems. These primitives work together to create the illusion of an isolated box. To the process inside, it feels like it's running on its own dedicated server. To the kernel, it's just another process with some specific constraints. Today, we are going to peel back the Docker abstraction and look at the raw kernel mechanics that make modern deployment possible. The first pillar of this illusion is namespaces. Imagine you are in a room with a window, but that window only shows you a tiny part of the street. You might think the street is empty, even if there's a parade happening just out of view. This is what namespaces do for processes. The PID namespace, for example, makes a process believe it is PID1, the master process, even if the host kernel sees it as PID 40528. There are namespaces for networking, which give the process its own virtual IP and routing table. There are mount namespaces that hide the rest of the host's disks. When you run a Docker container, the engine is simply calling the unshare system call. It tells the kernel, for this process, create a new view of the world. It's not a wall, it's a set of blinders. While namespaces hide what a process can see, control groups or Cgroups limit what a process can consume. If namespaces are blinders, Cgroups are a fence. Without Cgroups, a single runaway container could consume all the RAM on your physical server, crashing every other service. Cgroups allow the kernel to enforce hard limits on CPU cycles, memory usage, and even disk I/O. When you run Docker with the memory flog set to 512 megabytes, Docker isn't creating a 512 megabyte virtual machine. It's simply writing that number into a file in the sysfs cgroup directory. The kernel reads that file, and if the process tries to allocate more than its allowance, the kernel's out-of-memory killer steps in. It's an accounting system built directly into the scheduler. Before the fancy namespaces existed, we had Chroot. Developed in 1979, Chroot, or change root, is the oldest ancestor of the container. It does exactly what it says. It changes the root directory for a process. Normally, a process can see everything from the root / down, but with Chroot, we can tell a process that home user jail is actually the root of the entire system. The process can no longer see or access files outside that folder. However, Chroot alone is weak. A clever process with root privileges can easily break out of a Chroot jail. This is why Docker combines Chroot's successor, pivot root, with mount namespaces to ensure that the process is truly locked inside its own file system tree, unable to even see the host's bin or etc directories. If a container is just a process, where does its file system come from? That's the magic of union file systems like OverlayFS. Instead of copying an entire OS image for every container, Docker stocks layers. You have a read-only base layer, like Ubuntu, and then you stock your application code on top. When the container writes a file, it doesn't modify the base layer. Instead, it uses copy on write to create a new version in a temporary top layer. This is why you can start a Docker container in milliseconds. You aren't booting an OS, you're just mounting a new virtual view of existing files. It's efficient, it's fast, and it's why Docker images can share 90% of their data while appearing unique. So if the kernel does all the work, what is Docker? Docker is a management layer. It's the user-friendly interface that coordinates these low-level calls. When you type docker run, the Docker daemon talks to a tool called containerd, which then uses runc to actually trigger the kernel's namespace and Cgroup system calls. Docker manages the lifecycle, the networking bridges, and the image distribution. It turned a collection of obscure Linux features into a standard way to package software. You could build your own Docker in a few hundred lines of C or Go just by calling the kernel directly. In fact, that's exactly what tools like Podman or LXC do. They all use the same kernel primitives, they just put different clothes on them. Understanding that Docker doesn't exist as a kernel object isn't just a fun trivia fact. It changes how you debug. When a container has high latency, you don't look for a container bug. You look at the network namespace or the Cgroup throttling. When a file is missing, you look at the OverlayFS mount points. Docker is a brilliant abstraction, but like all abstractions, it is leaky. By knowing the truth of the kernel beneath, you become a better engineer, capable of seeing past the box and into the system itself. Thank you for watching. If you want to dive deeper into kernel internals, subscribe for our next deep dive on the Linux scheduler.